quite some time and accumulated a number of awards. I won't have time to read this all off, or if you won't have any time to talk. But Stu is an author of over 70 publications, 100 patents, and was recently won the National Academy of Engineering. I'm going to turn it over to Stu and let him talk about Fischer-Tropsh catalysts.
Good morning, everyone. Can you hear me in the back? Can you see me in the back? Okay. So I'm going to try to tell you today some of the learnings that we've had in over the years doing Fischer-Tropsh catalysis. The first part of the story is something that some of you may have heard before. We have talked a little bit about that. What are the main things that create the deactivation? Because this talk will be focused a lot on that. There'll be a lot of new material after that where we'll talk about how we try to design the catalyst, and actually how we try to make different ways of trying to make it. So we'll have a combination. If you haven't been around for a long time, some of the young ones, you probably haven't even seen the first part of this. Okay, I need to thank a number of people. You're going to find the imprint of my co-authors all over this presentation. Let's start with Sal, who you'll see a lot of the synthesis work. Gabor, who did a lot of the reactor studies and helped in the thinking and the formulation about the deactivation mechanism. Chris, who did a lot of all of the TEMs. And I particularly want to talk a little bit about Sebastian Reyes. So Sebastian was a chemical engineer, PhD chemical engineer from University of Minnesota that was with us for about 20 plus years. He was a brilliant chemical engineer. He left us all way too early. And this talk, actually, I'm going to dedicate to him. And as I put it together, I remembered all the times we had talking about this modeling, rather simple modeling that I'm going to talk about, and it just brought back some really nice memories. Okay, I also have to thank the organizing committee for giving me this opportunity. The strange thing about this, however, was they told me that we're only going to give it to you if you take it like really early in the morning. I said, how's that? They said, well, you have a little bit of a reputation. And we figure if we put you in the morning, then we won't have to sit through and watch you be doing this all, for the rest of the morning session. I said, well, you have to be careful about this because there's some scientific evidence now that this is actually very important. And here's a very recent article from the Huffington Post. And they actually call this, they actually have a name for it, the state between sleep and wakefulness, and it's actually your most creative time. And it even says down here that many artists have used this state to tap into their deepest creativity. So if you ever see me dozing, it only happens once in a while during any of your talks, it's only that I'm going into my very, very state of deepest creativity. And earlier this week, in addition, we did hear about one of the founders of our group, a brilliant person, and Paul Lemon. Okay, so Bert, who's sitting here in the front row, is the catalysis historical guru, and he wrote a story about Paul's life. And if you read through this, it said that he suffered from extreme fatigue, was told by a doctor to take short naps, a practice he followed for the remainder of his life. So here's an icon of our field, and he would do it too. So my only suggestion is keep your creative state, only get to it maybe at like 9:05, and that would be good. So try to delay that. Okay, so Fischer-Tropsh, and we're going to be talking about cobalt catalysts. So this Fischer-Tropsh is particularly the ones that we were interested in, of course, was over natural gas. And you can see, so a very simple reaction. It's a metal catalyzed polymerization reaction. And the interesting thing about it is that every time you create a CH2, you create a mole of water. The hydrogen, the oxygen is rejected as water. So that has a lot of consequences in this whole process. It has consequences on the energy recovery, and that the maximum thermal recovery you can get here is about 60-odd%, which means you're losing a lot of your energy that's in your methane when you do this. What you do gain, of course, is a product that has a lot higher energy density, and that's why there's an interest in doing it. But unfortunately, what it reflects then is and part of the problem we've had in this area is that as the economics change and the value of the liquid and the value of the gas keeps fluctuating, the value of doing this changes. And this is a long-term thing for industry to deal with. It's a huge investment, and while the prices and the differential is going like this, they get nervous about it. So this, I think, has inhibited a little bit of the application of it. The other consequence of the water is on the catalyst performance, and that's really dramatic. And we're going to see how that plays out a lot during the course of this presentation. So, as I said, we talked about some of the deactivation issues previously, and I'm going to just sort of summarize a little bit about that. So, one of the things that can happen is that you can have surface oxidation. So, from this water, the surface of the cobalt can get oxidized, and you can form essentially a cobalt oxide layer on there. That will inhibit the catalysis from going on. You can see that very clearly in TEM. So if you take, this is some TEMs. Now Chris, our TEM person, and Gabor had put together a wonderful cell where they could take the sample out of the catalytic reactor. It was mounted on a holy carbon grid, and then do a treatment in either a reduction treatment. You could actually run it, and they did run a little Fischer-Tropsh unit with a given amount of catalyst, with a given space velocity at a given temperature, at normal pressures, which is like 20 atmospheres, and then they could expose it for X amount of time to what the exit conditions were that you have during Fischer-Tropsh. And they could age the catalyst that way. Then Chris could take it back and put it back into a microscope and find the exact same spot she was at before. So you're going to see a lot of pictures where we have sections where we have it, the catalysis, the catalyst, sometimes before, sometimes here. This is removed from the unit, a treatment is done, and it's put back in the scope, and you can see the same exact spot. So that was extremely valuable. It's not in situ. I don't know that anybody, well, maybe, I'm not going to say that, things change quickly. Somebody will actually be able to run the Fischer-Tropsh in one of those cells and tie up the microscope for a few months. I'm not sure that's going to happen, but this is the next best thing, and it's very valuable. So here you see catalyst was taken out. This area over here with the blue circle looks fairly vacant. Once it's reduced, you see some of the small particles become visible again as you go back and re-reduce the smallest ones that have been subjected to the oxidation. So the good thing about this is that this is a reversible process. You kind of have to stop doing the syngas and go through what they call a rejuvenation cycle by putting the hydrogen in there and doing the re-reduction. But you can't get back your activity. Some of the other deactivation mechanisms are not so simple to reverse. So one that everybody has to be aware of is, of course, we have cobalt on an oxide, normally an oxide support. You create some of this oxidation. You can get some reaction between the cobalt oxide species and the oxide support. And this shows, this was a 6-month run where we took the catalyst out at the end of 6 months. And by doing very precise but very simple RO treatments, reduction oxidation, second cycle reduction oxidations, you can actually measure that very exactly. And we would see, for example, after the 6 months, that if we did a reduction back at 225 degrees C, the reason for doing that is that's a temperature you can reach in a unit. So you could always go back and say, okay, I can go up to that temperature. What loss am I going to have of available cobalt? And the answer is almost 10% over 6 months. So that's something that you can't recover, because once it's made these cobalt, whatever they are, whatever your support is, titanates, aluminates, silicates, they're not coming back. If you take it to a slightly higher temperature, you can get a little bit of it back, but still there's an irreversible loss here of about 6%. So that's one mechanism of irreversible loss. A second one, and the one that is really going to be the focus of the talk today, and is probably the one that we have to worry about the most, is the cobalt agglomeration, and that's the cobalt particles growing in size during the course of the reaction, and that, of course, lowers your activity. And so a lot of our work had been aimed at trying to understand how that happens, and as I'll talk later, how we can try to deal with that the best we can. Okay, so there are several methods of seeing that. Actually, there's a really, really simple one, and it was the way we first found out that we had this problem. Because we were seeing in various early runs in a bubble column reactor, we were getting losses of activity at various times. Sometimes there were issues with the bubble column. But you took the catalyst out, and you do a simple, again, reduction, oxidation, reduction, oxidation. And this is the oxidation cycle following the first reduction. So you reduce it, you actually then passivate it, because if you just put in the air directly to oxidize it, the thing would probably flame out. So you passivate it, you get some gain. That amount that goes on during that passivation step is it's not quantitative but it is kind of a qualitative guide of how many small particles of cobalt you have. It is akin to sort of an oxygen chemisorption, but oxygen chemisorption on cobalt is not really valid because the cobalt can oxidize past the surface. But you can tell from that even if you have a very dispersed catalyst or not. So that's just a qualitative thing. This is qualitative also, but it really can tell you. So this is just looking at the derivative of the weight change. And if you look at the starter run, which is this red curve, you see a pattern that comes here. And we focus mostly on what's going on once we get up to these higher temperatures. And we see when we took it out at the end of the run, and we did the same thing, the whole spectra shifts, and you get this tail at higher temperatures. So that's a consequence of the particles being larger and having a diffusion problem of getting the oxidation to occur. It's generally understood now to be the diffusion of the cobalt from the interior to the exterior surface that does it. But there were some where we would have big bumps here, and then you would see, you take this and look at it in the microscope and try to quantify what the sizes were, and you would see big clumpers, and they were very apparent from here. Now, one interesting part is, now we went back and took a catalyst like this, and then reoxidized it, then did a second reduction, second passivation, and then a second oxidation. And that second oxidation is reflected in this blue curve. So it says end of run and then air oxidized to 500 C. Now you see that this is shifted back, and some of those big ones seem to be gone. So at the early stages of this work, a lot of people thought this could be a way of regenerating the catalyst that might make sense. If you have particle growth, you would just have to go through an oxidation process and you could get particles back smaller. I will show in a little bit why that is kind of like pyrite, fool's gold. It doesn't really get you where you want to be, and that's part of what we're going to talk about, the big theme of this. Okay, so I said there's one method, there's another method, and this is some beautiful work that Chris had done. We had shown this before. So this is a catalyst at the start of the run. These are some cobalt particles, and I have to circle around these three. Now they're run in that little unit that G. Gabor put together, and now we look at exactly the same spot. This might just rotate a little bit, but this is exactly the same particles. And now they've come together. You can see over here the particles look like they're starting to neck. And then another 16 days after that, at day 48, now they've really come together. When you look down here, they're sort of sharing the common DNA. So this is the dance of the lovesick amoeba, as we like to call it. They come together. So we've had a lot of discussions with Abhaya. Is he in the audience here? No. Okay, so Abhaya talks a lot about ripening and a lot of, and there's a lot of processes that occur by ripening. We think this one is occurring by a different mechanism, at least in our hands, in these kind of units, and these kind of, practical conditions. And that is, it's a coalescence, but it's a coalescence induced by having the metal particles partially oxidizing, wetting the support, spreading, touching, and then sharing the genetic material, so to speak. And we're going to see more. And that's this pin the basis of the further part, the next part of the presentation on how we're going to try to fix things as best we can using, trying to realize that this is the mechanism. Okay, so this gets us to the point, if that's really the mechanism, then getting a very uniform distribution is really important. You have to really worry about it, not just the size of your particles, but how they're located on the support. And so you can see this is a fairly uniform sample. This is one that's made slightly differently, or substantially differently. And here the particles, they're smaller, but they're much closer together. And there are areas that aren't wetted so well. And when these two were run in our bubble column, and we looked at the particle size growth, and excuse me for not putting the numbers on here, this is about 6 months. These particle sizes went from maybe 10 to 16 nanometers in this case, or more than that. You could see that the smaller distribution started to grow faster, which normally isn't a surprise, but it also grew to a much larger extent. We've seen that in many cases when we've had cluster distributions, they grow more. They wind up at a higher. Now, a lot of times these growth and the deactivation does tend to level off, and we reach sort of a quasi-equilibrated state, so to speak, where it doesn't stop, but it slows down appreciably. Okay, so uniformity is important. Getting the particles there important. And so we have to be cognizant about all of that. Okay, now some situations are even worse. We talked about that regeneration, taking the catalyst, going through an oxidation at 500 and then coming back and reducing it. I showed you that on that DTG. This is what some of those particles look like. You can see there's really lots of little clusters. My buddy Enrique likes to call these graveyards. As I've gotten older, I've shied away from that term a little more than I used to. And here you can see it in detail. Chris captured it very nicely in the oxidized, a spent catalyst that's been air oxidized, and we saw the pictures. Brian's group reported this on Monday. You can see this Kirkendall effect where you get these hollow nano shells, and then they break apart during reduction, and it does actually make smaller crystallites, but those crystallites are really close together. So you can recover your initial activity, sometimes maybe even a little bit higher, but it doesn't last very long because they're so close together, they just coalesce very quickly. So that's why we say that's not the optimum way of doing the regeneration. Okay, so what are we going to do with all of this? How are we going to try to make our system better? How are we going to figure out what we really want? Okay, so to summarize a little bit, we said agglomeration, in our belief, is a major deactivation pathway. Coalescence, there's particles coming together, sort of speak by the oxidation and the wetting and the spreading. We're making the nanoscale uniformity important, and they do reach a quasi-equilibrated state. So this was the idea that we started to discuss with Sebastian, and we had a lot of fun trying to put this together and make some sense out of it. So the idea was to quantitatively compare some of the properties of the support that you're going to be using. Its surface area, its pore size, its pore volume, with the size and distribution of the cobalt crystallites on fresh and deactivated catalysts. So if we look at some that have reached this quasi-equilibrated state, what is it about them that happens? Well, you all know that as the particles start to grow, what happens is the distance between them starts to increase. And it looks like now, at a certain point, the system becomes a lot more happy than it was when they have separated by a certain critical distance. And that's kind of what we tried to look at. And the idea then was to see, okay, well maybe we haven't set up our initial catalyst in the best way that we possibly can. Can we take this, can we try to figure out what that distance is and then try to set up our initial catalyst so that the particles are separated by an appropriate distance from each other. And then maybe we can slow this down to some degree and not have some of this rapid deactivation that occurs by the growth. So that was the idea. Well, like I said, we wanted that particles will agglomerate when they reach a critical distance from each other. So this was the way the model was set up. We defined a virtual cobalt particle. So this is the real cobalt particle with the radius r, and this is the virtual one, lambda times r, so some multiplying factor of the radius. And then this becomes a critical distance. So we call lambda critical when lambda reaches a certain value where the particles are just touching, and at that point the system has reached a state where it's not going to coalesce as quickly. It's sort of equilibrated and happy at that point. So in a case here, now where lambda is less than the lambda critical, okay, because the particles are closer than the amount they want to be separated, then we're going to get coalescence and growth. On the other hand, once we reach this lambda being larger than what the critical distance is here, so here lambda will be larger than what the critical distance, the critical lambda will be, then we're going to limit the amount of growth. So that was the idea, and then the thing is, well, how do we find out what lambda is? Well, that's not so easy because these were done on catalysts that were run in bubble columns normally for several months. It's a big experiment. You don't have an awful lot of data that you can do this with, so we picked out what we had, and I'm going to show you that on the next slide. And so here's a catalyst one that we'll talk about. That was a very nicely wetted catalyst. It started out with a lambda, and we went through all this formulation with Sebastian of figuring out the distances that we had depending on the sizes of the particles, the distribution of the particles, and the surface area of the support. And we start out with a lambda of about 2.25. So in other words, the particles are within, on average, 2.25 radii of each other. And then we see as we go through deactivation and it reaches this 189 days where it's semi-equilibrated, the lambda goes to about 3 approximately. So 3 times the particle radius. And then it seems to quiet down and be a lot happier. So then we took a second catalyst that was run. This is a higher loaded one on a higher surface area support. This wetting was not as good at all. So what we did to try to compensate for that was to put a homogeneity factor of how much of the support is being used. Because of course if we're only using some fraction of the support, then the particles are going to be closer than they would if we used all the support, everything else being the same. So when we did that, we wound up with a lambda that came out to be about 3 again. And then we had a third catalyst. This one was made differently. It had a particular dispersionate in there. It gave a very different distribution, a lot smaller particles. It grew very quickly. This is one of the ones that we showed before. And again, when we put in this wetting factor of 0.8, we came out again around 3. Then we had another catalyst, which was actually this first one, which we annealed. We annealed it in an inert environment to sort of pre-grow the crystals to a given size. And we saw that that size gave a lambda of about 3.3. We did get a stable run. Of course, it had lower activity than up here, at least lower initial, because we had grown the particles. But it kept landing around this value of about 3 as an approximate value. Okay. So that sort of told us the spacing that we needed to have. Now, is that reasonable? So if we take a 100 angstrom sphere, for example, and we sort of squish it down and let it grow out to 3 times its radius, so 150 angstroms. Okay, 150 angstroms. We're going to get a height of about 7.5 angstroms where we have lambda equals 3. So that's kind of neat. I thought that was kind of interesting when we did that, because now that means we have actually wetted. The particle has really shrunk down. We've really, this would be then, the idea is that this would be the metal, this would be when it really substantially starts to oxidize and wet the support. And we're saying within that distance, if there's another particle that we can touch, it maybe start to grow. So this makes some physical sense, that we kind of have essentially a monolayer or a little raft of the oxide or the hydroxide that we form of that size. Okay, so consistent at least with what we're trying to say. And so that's just what I said. Now, when we were doing this work, this was quite a while ago. Actually, we were still pretty young at the time. We realized in work we had done earlier at Exxon, actually when Enrique was there, that really small cobalt particles down at a couple of nanometers, they didn't work well at all. We didn't totally understand it as well, as much as maybe we should have. But in the intervening years, there's been a lot of really nice work to understand that better experimentally and to understand that better calculation-wise. And I'm going to just touch on that for a moment. So over the last number of years, there's been a lot of papers from Brian and his group at Utrecht that cobalt particles less than 6 nanometers have lower intrinsic turnover rates, Fischer-Tropsh, and very nice work, in my mind, very conclusive. And then more recently, Matt Neuron has published some and explained this from some of his calculations, and I think he has a talk to either later today or tomorrow where he's going to describe some of this. And he rationalized that by saying that the CO is much more strongly bound on the edges and the corner sites. And we have obviously a lot more of them as the particles get small. It creates higher CO dissociation and activation barriers, and the CO binding is significantly stronger at the edges and the corners. and that makes it more difficult to remove the CO and the fragments, and the sites become blocked and poisoned by these. So that's nice. What it's telling you is that there's a boundary on how small you can go. We're saying now there's also a boundary on how you have to place these particles and how you have to space them. So we're starting to see maybe a little bit of a window where we have to operate in, and that's what we tried to quantify next with Sebastian. Okay, so we started to introduce this idea of making these phase diagrams. Very rough use of the term when you get it. So here on the x-axis we would have the percent cobalt loading. On the y-axis we would show the size of the particles. And we would basically have regions, given what the support properties were, what the surface area was, and whatever, it would determine how these looked. And I'm going to show you some examples of these. So this is just a generic way. And then we would have an area over here. Obviously at high loading and a small particle size, we get into cases where the particles get closer together. So here we're at lambda less than lambda critical, and we'll get coalescence. As we start moving to smaller, lower loadings and larger particles, the distance becomes larger, and we wind up in this lambda critical. Okay, so what if we start over here? Maybe it would help. And so we also have boundaries. This is what I just showed. You have a certain size, around 6 nanometers. You don't want to be lower than that. You also probably have a boundary condition at the top, in that the particles, which are normally on this order of 70, 100 angstroms in size, they have to fit into the pores of the support. If you have a support that has smaller pores than the size of the metal particles, they're not going to get in there, and you're going to have, obviously, if it's just barely larger, you may have trouble getting things in and out. So you have to give yourself some room so that this ratio of the particle size to the average pore size does have to be in a certain range. And you can get into problems if the particle size becomes larger than the pore size or the multiple of the pore size that you're working with. So now we sort of have some boundary conditions. So let's look at some specific examples. So here's one where we've taken a cobalt particle that's been loaded at 11%. And this is on a support of about 15 meters squared per gram. Why so low? Because this gives us a large pore diameter between 4 and 500 angstroms. Plenty of room in there to get the particles, plenty of room to wet it, plenty of room to get your reactants in and out. The problem is, this is in the lambda, less than lambda critical region. So as you start to run, the particle will start to grow and move in this direction towards lower activity until it gets into a state where it will equilibrate. So what if we move off of that? And what if we move it into a slightly higher surface area? Here we're going up to 30. Okay. Now the catalyst is just barely on the other side. The pore diameter is shrunk a little bit. You probably can still manage here. It's gone to maybe 3 times the pore size versus the cobalt. And so this is sort of telling you where your boundaries could be. Now if you go up even higher, this is the case of 60 meters squared per gram. That puts you squarely over here, but now your cobalt radius relative to the average pore radius is coming up to about 1 to 4. That's probably still okay, and it depends. In this particular case, we actually we let the pore volume get a little bigger to accommodate a little bit larger pore diameter. But by looking at these values, you can kind of pick where you are and get things in the right spot, or maybe closer to a spot where we'll be happy. So it starts to define the window and the boundary, and in some degree, the limitations that you could ever have at a given site activity for one of these systems. Because you're going to have a boundary. You're not going to ever get to super, some activity way higher than you think you have unless you change the intrinsic site activity of your particle, which is not easy. Okay, so that's the preliminary conclusions, that for an optimum support surface area between maybe 30 and 60, with a 3 to 400 angstrom pore for about 11% cobalt loading, 10% dispersion, in other words, 100 angstrom cobalt crystallizing, and you have excellent uniformity, so you've wetted the surface very evenly. Things get worse, again, if you have regions where you haven't wetted. Okay, so that was the hypothesis, and now the question becomes, okay, there is an issue here too, that this was based at runs that were done in the region of maybe 60% conversion. water and the amount of water has a consequence, and a big consequence. And this was some data that Bohr had taken in a fixed bed reactor, where he saw that the catalyst would actually grow a lot more towards the exit. It depends on the catalyst, but they always would grow more towards the exit. Some would grow more than others because you have a higher water partial pressure there. So that's another sort of global superposition on top of everything. It does depend on where you are and what your water partial pressure is. Okay, so now the experimental challenge is how are you going to try to make these samples to fit into these support boxes that you have, and what are your approaches to try to make it uniform or whatever. So I'm going to just talk a little bit about that and some of the approaches. There's an awful lot of work going on these days in catalyst synthesis and whatever, and there are many ways of trying to wet surfaces, produce interactions between the support and the precursor, electrostatic absorption, using complexes, and so on. And so some of them, I'm going to show you here very quickly. So again, the question was, how do we load the cobalt uniformly? And how do we prepare them based on the quantitative guidance? And then we also have this issue, and this is a very complicated system. There's also oftentimes a promoter in here. It's often a noble metal, and it serves several functions. It helps reduce the catalyst. It also tends to make the preparations, in many cases, you get smaller crystals, and it does help in many things. But the problem is they cost a lot of money, these noble metals. You'd like to decrease their amount. Okay, so the classical behavior of that is you get your promoter content higher, you get a higher relative activity, largely because you make your cobalt crystals smaller. I mean, there are some cases where you can kind of get an intrinsic site activity improvement with the promoter, but in most cases this is just due to a size effect. But you'd really like to have a much lower loading. It makes it more difficult to do this homogeneous preparation. That's all. So you just have to be aware of that as well. So let's talk about now. So here's here's one way. So here's one, actually the lower promoter loading, where we did use a particular organic, and actually we got a very nice distribution. So this is a very legitimate approach. The problem with this, you have a fairly high loading of metal, you put that organic in there, and now you have to oxidize it. So as you start to do scale up on that, now you get issues with exotherm, sometimes with what the products are of oxidation. So if you could avoid this, it's probably better. This is fine for making lead catalysts, but in scale up, this can be an issue. So what else can you do? Okay, so there was some nice work. Actually, this happened after some of the things that we had done, but it speaks very much to the point I want to make. So it's again some work from Brian's lab, where he showed that the role of the atmosphere and in which the particles are created. And this one, I just picked one out with nickel on it, where he did calcinations followed by reductions, and the calcinations were done in different environments. They have papers with cobalt showing very much the same thing. And if you do it in nitrogen, you do it in stagnant air, you get things that don't look very well. This is on one of these SBA 15s. But if you had NO present, you would get a nice distribution. So the bottom line is the atmosphere and the details of changing the precursor into, say, the supported oxide are very important. And we saw that very clearly in our system. And I'm going to show you that on the next one. So this was really cool. And we worked largely with a specific support. It was a support that contained multiple oxide components. One can refer to some of the patents that are out there from ExxonMobil to see exactly what that was. It had a large titanium component. There were other things in it. So there are some nuances to that support that are maybe different than what you have with a single component ones. But in any event, so here's a combination of TG, DTA, mass spec. So here's the TG curve, and it has some bumps in it. When you look at the DTA, you see this dual endotherm during the reduction of the cobalt nitrate. So whenever we say things like this, we always like it because something's happening between there. And you can actually see, if you look at the products, water comes out only during the first endothermic decomposition. Now water's coming out here just during the drying. It's also coming out at these higher temperatures in a very discrete packet at the same time as the NO and the NO2 seem to be coming out. And then we have a second step where we just get NO and NO2 and water. So it was like, okay, that's cool. What if we play with this now and try to see if we do some variations in the lifetimes of the states we're creating at the NO and at the two different the two different endothermic decompositions. The idea being, can we get in some of this, are we making a state of this which is just really nitrate going to oxide that itself might wet the support the same way that the oxide, that the organic and organically modified precursor might wet the support. Enhancing that wetting of the support is something that helps to distribute it more. And that's why the organic addition works so well, and everybody does it in many different things. So how to get around that? This is cool, because now we can maybe get away and just use the nitrate, or some form of the nitrate that's wetting the support. And in fact, it did play out that way. So this is a sample where the precursor, we take it through the first nitrate endotherm and hold it there. We held it there for something like 30 minutes. And then we continued up. And we got a decent, a pretty good distribution by the way things go. And here's one, come on, there we go. Here's one where we just hit it directly through the two decomposition steps. There we would have some pods that are reasonable there, but there are a lot of pods where we would have dense mixtures and some that didn't seem to be wetted very well. So it seemed to be a lot better if you did that. That's in the case of having a large amount of the promoter. Okay. Now we said we stress the system when we go to low promoter. It becomes much harder to get the distribution. So what we did there was, if we did the same thing and held it after the first intermediate step, it's not horrible, but it's not really all that good. But now we took it after that first step, removed the sample, and actually put it in a very humid atmosphere and let it sit there for several hours. And in doing that, and then took it back up the same heating rate as before, and we got a much nicer distribution. So it looked like there was some sort of hydrolytic decomposition that was going on. And that it was, we were creating something, we were locking it in, and then we were decomposing it. So what was that? So in order to try to understand that better, we got some in situ infrared measurements that one of our colleagues who used to work with Malki created, and he really saw some spectra that seemed to really talk to the situation. So if particularly you look at this region over here, which we take this blue region, as signatures of nitrosyl. Now I'm not going to argue very hard that this is nitrosyl. I mean, the group from Utrecht talks about hydroxynitrates. But the point is, we do get very strong signature peaks when we go up to this first step of the decomposition at 160 degrees that weren't there when we were at lower temperatures. And then when we keep it there and we expose it to water for different periods of time, they disappear. So it really looks like we're making some intermediate, without using organics, some intermediate that is wetting and spreading on the support and then going away as you go up to higher temperatures and convert to the oxide. Okay, so I think I'm just about at my end. So I have a very quick summary. I hope I tried to convince you that coalescence is often the major contributor to FT deactivation. That's been our experience, and that coalescence seems to relate to uniformity, to spreading and wetting the surface of oxide, hydroxides, and then forming into metals. And therefore, controlling metal nanoscale homogeneity is one key way to try to improve the stability from the beginning of the run. And therefore, controlling the support and metal properties and having them be chosen and adjusted with the critical boundaries in mind and with definite limitations that you impose on the system to try to limit the coalescence is a very interesting way to go. And what I tried to show is that the details of the cobalt precursor support interaction can be critical for the creation of a dispersion, uniform distribution, and lowering the promoter concentration. And after you go through all of this, and we spend 100 years studying Fischer-Tropsh, we all humbly say, we understand maybe a little bit. So with that, thank you for your attention. And now you can take me back.